Okay, so let's get started. We're going to be taking a look in this tutorial at understanding the relationship between our GDI, gasoline direct injection, and port fuel injection found within the same fuel system here on our Gen 3 Coyote engines. So whether you're tuning a Mustang or an F-150, understanding how the system works in detail is critically important, especially if you're going forced induction, for example, putting on turbochargers, putting on a supercharger kit. You're going to find that you're going to be limited in how much fuel flow you have available, and you always want to take advantage whenever you can at high loads of your GDI system for the charge cooling effect and knock suppression that it provides. So what we're going to do here is learn some of the stock programming, how Ford calls things out, how Ford programs on a stock engine. Future tutorials will talk about how we can use the GDI and port fuel injection at a higher power levels. So again, forced induction will make a little bit more sense of that. This is just going to be digging into the stock logic and the tables that are associated that we really have to touch for our programming to get the most out of the GDI and the port fuel injection system. Let's jump in here and open up a stock equivalent file. We'll talk about the tables of interest here and how some of this works. Then we're going to relate this back into some logged data through the VCM scanner so we can see what we may need to adjust or how our fuel systems are performing for both GDI and for port fuel injection. All right, let's jump in. Let's open up a stock equivalent file here. I'm going to go up to File. I'm going to go to Open and move into my course folder. Let's go to HPT Gen 3 Coyote. And we're going to move in here to our sample calibration files. And then in here, we're going to move down into our 2020 Mustang GT Auto stock. Any of the stock files will work here. We don't want to open up a Roush or Whipple file yet. We will take a look in another training module comparing a stock strategy to something that Roush or Whipple is going to command, because it changes the relationship between the direct and port fuel injection. And it's specifically done in that manner because most people aren't upgrading their GDI high pressure mechanical pump to an aftermarket unit because they are extremely expensive, but we will cover changing that out and some topics with that at higher power levels if you want to stick to GDI more heavily under load. But let's open up a stock file right now to keep things simple. Okay, I'm going to open this up. We're going to go in here to our engine tab. We're going to go here under our general, over to fuel, over to general. We're going to specifically focus on our DI-PI blending in this training module and just discuss what we have going on in here. But we will be referencing and talking about also our DI injection timing. Now, we did have a tutorial talking about our DI injection timing, understanding the start of injection and end of injection within the GDI operation, and that narrow band that we have to get our fuel in, and understanding how the GDI system operates at very high pressures, and making sure we understood just the general overall overview of looking at the GDI system. So now we're going to be coming back in here and talking about that when we look at some of our log data. But let's talk about our DI-PI blending. So what we find here is that we have a ton of different things that we could program. We mostly will stick to editing our warm and cold tables here. And more specific, we're likely just to edit our warm table. What this is going to do here, if we're looking at our warm table, this is going to be based on engine speed versus engine load. Engine load is going to be based on air mass registration. So load is air load, which is a function of air mass, which is a function of the MAF or the speed density within the operation of the engine control module. So more airflow, more load, higher engine speeds. Obviously, we can see here the table has this three-dimensional shape. Now, looking at this table, it's actually really simple to break this down. If we call out 0 in the table here, that means that we're running just on port fuel injection. If we call out 100 in the table here, that means that we're just running on the GDI or direct injection system. If we call out something like 50, this is splitting the fuel flow that we have to deliver into the engine 50% through the port fuel injection and 50% through the GDI or high pressure injection. So how does this actually work? In case you're wondering, how does it actually deliver the proper fuel flow through each set of injectors? So we have our direct fuel injectors and we have our port fuel injectors. So the port fuel injectors are operating anywhere between roughly 55 to 75 PSI, while the direct injectors can be operating anywhere from 900 to about 2,900 PSI. Well, we have injector characterization data. So we find over here, we have our low pressure port fuel injector characterization data. And we're going to be talking about how this works in a couple tutorials coming up here in the training course. But this is essentially translating when we request a certain amount of fuel mass to come in to be injected into the engine, which is based on how much air mass we have coming in. So air mass and fuel mass are going to be proportional to each other. If we have more air mass, we need more fuel mass. Less air mass, less fuel mass. So this allows us to translate when we have a certain amount of fuel mass into an injector pulse width, characterizing the response and the flow rate and all the details with our port fuel injectors. That's going to be found here. We're going to find that same characterization data is going to apply to our direct fuel injectors, which is going to be found in here. So what we're going to find is that when we've specified the blend ratio here, 0 or 100 or anything in between, we know what the air mass is entering the motor. Therefore, we can calculate the fuel mass. The fuel mass gets converted into an injector pulse width based on knowing, first, the split that we're commanding here between both set of injectors, then looking at the flow rate of the injector and the characterization data, such as the dead time latency data, or offsets called, and it's going to be then sending that as a pulse width to each set of injector. As long as our injector data is programmed right, we'll deliver the fuel mass that we're requesting in relation to the air mass the engine is ingesting and we're registering. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.